Adam Riess was 27 years old when he began the work that would earn him the Nobel Prize. He was not, by any measure, the most obvious candidate. He had grown up in Warren, New Jersey. His father sold chemical compounds to pharmaceutical companies. His mother was a psychologist. Nothing in his upbringing pointed toward the edge of the observable universe. What pointed him there was something simpler. When a number didn't add up, Riess couldn't stop until he understood why. Not wouldn't stop. Couldn't. In 1998, on the eve of his honeymoon, a number came back that didn't add up. He has spent the 26 years since trying to understand why. He has not stopped. This is not a story about the expansion of the universe. You have heard that story. The universe began. It expanded. Something pushed it apart. It will keep expanding until every galaxy disappears beyond the edge of what we can see, and what remains will be cold and thin and still. This is a story about one number, and the fact that two of the most precise instruments ever built by human hands cannot agree on what that number is, and what that disagreement might mean for everything we thought we knew. In the grand story of the cosmos, the late 20th century felt like a time of consolidation. We thought we were getting a handle on the big picture, and at the heart of it all was a single, fundamental question. In 1998, two independent research teams, working on opposite sides of the globe, were trying to answer it. How fast is the universe expanding? And, more importantly, is it slowing down? The assumption, the bedrock of all cosmological thinking, was that it was slowing down. It had to be. Gravity, the universe's oldest and most patient force, acting across billions of light years, pulling matter back toward matter. The universe, it was thought, was like a ball thrown into the air. The initial explosion of the Big Bang was the throw, and gravity was the force pulling it back down, losing momentum over time. This was not speculation. It was the prediction of every major cosmological model in existence. The only real debate was whether the universe would slow to a stop and collapse back on itself in a big crunch, or simply slow down forever, coasting into a cold, dark eternity. To measure this cosmic slowdown, Adam Riess and his team used a specific kind of dying star to test it, a Type Ia supernova. These are the gold standard of cosmic measurement, what astronomers call a standard candle. They occur in binary systems where a dense white dwarf star siphons material from its companion. Once it reaches a precise critical mass, it detonates. These stars explode at a predictable brightness, all of them, every time. This incredible consistency means you can calculate exactly how far away they are based, solely on how bright they appear through your telescope. The dimmer the explosion, the more distant the galaxy. It's a yardstick for the universe itself. They measured 42 supernovae, 42 pinpricks of light from the edge of the observable universe, across billions of light years. Each one a message from the deep past, a fossil of cosmic history waiting to be read. This is what that work actually looks like. It's not a single eureka moment, but years of patient, meticulous effort. You identify a galaxy you have already mapped. You watch it every night. You wait. And one night, something in it explodes, a star at the end of its life, releasing in a few weeks the same energy our sun will produce across its entire 10 billion year existence. A brief, impossible beacon. You photograph it. You photograph it again and again. You measure the brightness at every stage of the detonation, charting its rise and fall with obsessive precision. And then you subtract. This is the unglamorous, essential heart of the work. You subtract the light from surrounding stars. You subtract the glow of the Milky Way. You subtract the distorting effects of Earth's own atmosphere. You account for interstellar dust clouds between you and the explosion, each of which absorbs a fraction of the light before it reaches your sensor. You correct for the fact that the hundreds of thousands of pixels in your camera are not all identical. Each one captures light slightly differently, and those differences must be cataloged and removed. It is a process of purification, of finding one true signal in a universe of noise. Riess spent years doing this. His team spent years checking Riess doing this. Every calculation was scrutinized, every assumption questioned. This is the soul of science, not the flash of insight, but the relentless collaborative effort to prove yourself wrong. When the final data came together, after all the subtractions and corrections, the result was not just wrong, it was impossible. He described the result, his exact word, as shocking. The distant supernovae were dimmer than they should have been, which meant they were farther away than predicted. The galaxies were not decelerating, they were accelerating. Something was pushing space itself apart, faster and faster, with no friction and no ceiling. Something that had no name and no mechanism in any existing theory of physics. It was as if the ball thrown into the air had suddenly sprouted rockets. This immediately suggested a profound conclusion, he said years later at his Nobel lecture. The expansion of the universe is not slowing down due to gravity, but is instead accelerating. They gave it a name anyway, dark energy, which is less a description than an admission, a placeholder for our ignorance. We do not know what this is. We know it is there. We cannot find it. That discovery, the most profound in cosmology in half a century, delivered in an email with an understated subject line, on the eve of his honeymoon, earned Adam Riess the Nobel Prize in Physics in 2011. It was a recognition not just of a shocking result, but of the years of painstaking work required to believe it. He went back to work the following Monday, because the prize wasn't an end. It was the beginning of a much larger, much stranger mystery. Here is where the problem begins. The expansion rate of the universe, called the Hubble constant, can be measured in two fundamentally different ways. You can look outward, at supernovae, at Cepheid variable stars, pulsing at known frequencies across nearby galaxies, at objects moving through space right now. This is the cosmic distance ladder, Riess's method, his number refined over decades, 73 kilometers per second per megaparsec. Or you can look backward, at the cosmic microwave background, the oldest light in existence. The afterglow of the Big Bang, still visible in every direction, cooled over 13.8 billion years to just barely above absolute zero. The Planck satellite measured this light with extraordinary precision and extrapolated forward using the standard model of cosmology. That number, 67 kilometers per second per megaparsec. 67, 73. The difference is 9%. In most scientific fields, 9% would be rounding error. In cosmology, where measurements have been refined across decades, cross-checked against multiple instruments, verified by independent teams on multiple continents, 9% is not a rounding error. It is a 5 sigma discrepancy. 5 sigma is the threshold at which scientists stop calling something a coincidence. It is the threshold at which they are required by their own methodology to take it seriously. It means that if both measurements are correct, there is a 1 in 3.5 million chance the difference is random noise. There is another possibility, which Wendy Friedman, one of the world's leading experts in the cosmic distance ladder, has advanced publicly. Friedman's measurements using different calibration methods return a number between the two. Not 73, not 67, something closer to 70. Her interpretation, the tension in the data is smaller than Riess claims, that it is too soon to name a culprit. She wants more data before deciding whether the problem lies in Riess's measurements, the standard model, or something else entirely. The debate between them has been, by all accounts, vigorous. Adam speaks very loudly, said David Spergel, president of the Simons Foundation. He argues vociferously with whoever disagrees with him. No one, however, has found an error. Scientists have a name for the space between the two numbers. They named it, as they name most things they cannot explain, carefully and without drama, the Hubble tension. For years, the assumption within the field was that Adam Riess had made a mistake. It was, by far, the simpler explanation. In science, when a single result contradicts a vast, established body of knowledge, the most likely culprit is the new result. One team, one dataset, one undiscovered systematic error. That's where you look first. Find the error. The tension disappears. The standard model of cosmology, our fundamental understanding of the universe, is safe. The entire scientific community was, in a way, counting on it. The James Webb Space Telescope was, among many other things, the opportunity to find that error. JWST took 20 years and $10 billion to build. It was designed to see the universe in infrared light, to peer back through time to the very first galaxies. To do this, it had to be placed 1 million miles from Earth, far from our planet's heat and light. It carries a primary mirror the size of a tennis court, composed of 18 gold-plated hexagonal segments that had to unfold perfectly in the cold of space after launch. It has 344 individual components, any one of which, if it had failed, would have ended the mission entirely. Engineers called them single-point failure events. It was the most complex machine ever sent into space. Every one of them worked. With the telescope operational, Riess used JWST to re-examine the entire chain of measurements underlying his 73. He and his team, Riess, went back to the beginning, recalibrating the cosmic distance ladder step by step. They used 3 independent calibration methods. The full range of what Hubble had observed, now checked against a far more powerful, more precise instrument, free from the atmospheric distortions and background noise that can plague ground-based and even lower-orbit telescopes. This was the final check, the ultimate arbiter. "We've now spanned the whole range of what Hubble observed," he said after the results came back, "and we can rule out a measurement error as the cause of the Hubble tension with very high confidence." The number came back at 73. The error wasn't in the measurement. The discrepancy was real. "With the errors eliminated," he said, "what's left is the possibility that we have misunderstood the universe." The field absorbed this. The tension was no longer a potential error, it was a confirmed paradox. And then, in March 2025, something else arrived. The Dark Energy Spectroscopic Instrument, 5,000 robotically controlled optical fibers on a mountaintop in Arizona, each one locking onto a different galaxy every 20 minutes, released the results of its 3-year survey. This wasn't about measuring the expansion rate. DESI was built to map the history of that expansion over billions of years. It produced a staggering cosmic cartography, tens of millions of galaxies, the largest map of cosmic structure ever assembled. The signal it returned was not expected. When scientists compared DESI's map to the predictions of the standard model, the data didn't quite fit. There was a deviation, subtle but statistically significant. Dark energy. The force Riess discovered in 1998, the force that earned him the Nobel Prize, the force the standard model treats as a fixed and permanent property of empty space, a cosmological constant, may be weakening. The data suggested that this force, which has been pushing the universe apart at an ever-increasing rate for the last 6 billion years, might not be constant at all. It might be running out of steam. It smelled, Riess told The Atlantic, like something might be wrong with the standard model. This is a profound shift in our understanding of the cosmos's ultimate fate. If dark energy continues to weaken, if it drops to zero, if it turns negative, the universe will not end in cold silence. It will end in collapse. The expansion will slow, stop, and then reverse. Every galaxy, every star, every structure that exists will fall back toward a single point, the same kind of singularity that produced the Big Bang. A big crunch. The standard model did not predict this. It has no explanation for it. 2 major independent observations, one looking at the present-day universe, the other at its history, are now pointing to the same conclusion. Our best theory of everything is incomplete. It's broken. Imagine you are Adam Riess. You are 27 years old. You are measuring the distances to dying stars in galaxies billions of light years away. You have learned, through years of work that mostly led nowhere, to distrust what your instruments tell you. You have learned to assume you are wrong. The data almost never says what you want it to say. Most measurements are mistakes. The data comes back. You run it again. You ask someone else to run it. You correct for dust, for noise, for sensor variation, for galactic glow. You subtract everything that is not the supernovae. You are left with a number. The number does not make sense. You send an email on the eve of your honeymoon. Your new wife watches you type and asks if this is how life is going to be. Is this the way our life is going to be, that you're always working? You tell her this is a special email. 13 years later, you stand in Stockholm with a Nobel Prize. You have confirmed dark energy. You have, by any reasonable measure, found the thing you were sent to find. My confidence peaked in 2011, you will say later, because we won the Nobel Prize. You go back to the telescope. The number still does not match. You spend the next decade refining your measurement. You wait for JWST, 20 years in the making, 344 potential failure points, $10 billion of human ambition pointed at the sky. You use 3 independent methods. You ask the most powerful telescope ever built to prove you wrong. It comes back with 73. You are 55 years old. You have a Nobel Prize for discovering something you cannot fully explain. And now the number you measured to win it may be pointing at something larger, a crack in the framework that physics built over a century. You are asked in an interview what you actually understand about dark energy. You pause. Wow, you say. That's a good question. I don't know that I ever contemplated it at the time. I think it was mostly, is this right? Is this right? You are still asking the same question. You have not stopped. The standard model of cosmology is not a guess. It is a monumental intellectual achievement, known to physicists as lambda CDM. Lambda for dark energy, the force driving cosmic acceleration. CDM for cold dark matter, the invisible scaffolding upon which galaxies are built. For half a century, this model has been our guide to the cosmos. It is the most rigorously tested framework in the history of science, supported by independent observations from dozens of research teams across decades. It correctly predicted the large-scale structure of the universe, the distribution of galaxies, the temperature of the oldest light in existence. It has passed every test thrown at it with flying colors. It is not easily discarded, and yet, for all its triumphs, it cannot explain a 9% difference in one number, a number that defines the entire scale and fate of our universe, the Hubble constant. This isn't a rounding error. In a field that measures the echo of the Big Bang to parts per million, a 9% discrepancy is a cataclysm. It is a fundamental break in our understanding of the cosmos. The implications are staggering. Either something about the very early universe is not what the standard model says it is. Perhaps a new form of energy existed for a fleeting moment after the Big Bang, changing the cosmic rulebook before vanishing without a trace. Or dark energy is not the constant force that physics assumed. Maybe it is dynamic, evolving, growing stronger over time, pushing the universe apart faster today than it did in the past. Or there is something in the structure of the cosmos that does not yet have a name and does not yet have a place in any equation currently written. A new particle, a new force, a flaw in our understanding of gravity itself. Riess believes the tension will grow more pronounced. He believes more cosmologists will begin to question the standard model. He has reason to hold that belief. He came of age in a field that told him, based on the best available evidence, that the universe was decelerating. It was the consensus, the bedrock assumption. He measured it himself and found the opposite was true. He, along with his colleagues, discovered that the expansion was speeding up, a finding that would earn him the Nobel Prize and introduce dark energy to the world. He has learned not to trust comfortable explanations simply because they are comfortable. "I'll be totally honest with you," he told an interviewer in 2025. "I think the ultimate answers generally come from theorists. People like an Einstein who sit there and synthesize this and say, wait, here's what's really going on." He sees his own role with a clear-eyed humility. He is not the one to build the new cathedral of thought. He is not a theorist. He is the man who measures. His job is to provide the facts, to map the terrain with ever-increasing precision, to deliver the clues. He measures, and what he finds goes to the theorists, and the theorists have not yet found the answer. The data is a challenge, a gauntlet thrown down. And for now, the theorists are stumped. But something is shifting. The quiet confidence of the standard model is giving way to a thrilling, anxious uncertainty. "When there's no big problems and everything's just kind of fitting, it's boring," Riess said at a cosmology conference in 2025. "Now among my colleagues I could feel a new buzz. The daggers are out. A fight is brewing. The field is hot again." He paused. A new universe suddenly seems possible. In cosmology, there is a word for measurements that cannot be reconciled with each other. Tension. It implies two things, pulling in opposite directions. Two different, highly precise views of the same universe that refuse to align. It is a sign that the picture is incomplete, an unstable situation, something that will eventually give. The Hubble tension has existed in its current form since approximately 2011. For over a decade, it has been the central drama of cosmology. It has survived every new instrument. It survived Planck, the European mission that gave us our most detailed baby picture of the universe. It survived JWST, whose infrared eyes sharpened our view of the local cosmos. It survived the largest galaxy survey in history. With each new observation, with every supposed systematic error that was hunted down and eliminated, the tension has grown more pronounced, not less. The crisis has deepened. Somewhere in the gap between 67 and 73, in those 6 kilometers per second per megaparsec that no measurement can close, something is hiding. A truth about the universe we have not yet grasped. It is a small number that represents a vast gulf in our knowledge. We do not know what it is. We only know that our model of reality is missing a piece. We know it is there. Science has a word for the current status. It is not failure. It is not wrong. It is a word that signals the edge of the map, the frontier of discovery. The word is unresolved. End production notes. Довжина H 2752. 21-22 минути при Orbitalus tempo. Верифицирани цитати, всички реални.